In this lecture, we will complete deterministic parsing and start probabilistic parsing. One question that might arise in our mind is why should we worry about probabilistic parsing? Why bring in probability? What is probabilistic about parsing? The answer to that question is that natural language sentences are ambiguous by their very nature. There is ambiguity with respect to words. Words can have multiple meanings and only one meaning is applicable in a particular context generally. And there is also structural ambiguity where phrases, clauses can have multiple attachment points. A very famous example is the example of I saw the boy with a telescope. With a telescope is a preposition phrase which can get attached to boy, meaning thereby the boy has the telescope, or it can get attached to see, meaning thereby that I had the telescope. I saw the boy with a telescope. Now, the point is that this attachment of the preposition phrase is a structural question. In which part of the tree does it exist? What is its parent node? So, sentences, the sum and substance is that sentences can have multiple parses. So, this is the ambiguity issue, and now we have to choose the best possible parse tree as the dictate of the context or the discourse is. So, now the question is, when we have multiple parses and we have to choose one, on what basis do we choose a parse tree? So, here comes the notion of a scoring function. We have to score the parse trees and choose the one which is the highest score. This score is often in terms of probability values. The probabilistic framework provides a systematic platform by which this kind of scores can be computed, and probabilistic parsing takes its birth in this notion that ambiguous sentences are a reality. Choosing amongst ambiguous sentences is also a reality. How do we make this choice is a matter of scoring those trees, and probability provides a principal way of arriving at this scores. All right. So, now we take the first step of discussing how to parse an ambiguous sentence. The three algorithms we discussed, namely top down, bottom up and top down bottom up chart parsing, can they produce multiple parse trees when structural ambiguity exists, and how do they appear? All right. So, parsing ambiguous sentences and probabilistic parsing is the topic. So, just to recapitulate the top down bottom up parsing, we said that when we have a sentence like people laugh loudly, we first have the transitive closure of the non-terminal in front of dot. So, non-terminal expanded to dt n and n, thereby exposing dt and n. So, since we have to look for a noun or a dt, we find a noun here in people, and that finishes the noun phrase. When the noun phrase is over, then VP gets exposed. VP's work requires finding a verb. Now, verb has been found in loudly. So, then adverb gets exposed, and now we need to find the adverb. Loudly is that adverb. So, now the verb phrase is over, and the verb phrase for the sentence is also over. Now, as the grammar goes, since a VP is over here, we could also finish the sentence through noun phrase and verb phrase at this step. And indeed, this is the case, because people laugh is also a valid sentence. But we cannot signal the end of parsing or success of parsing, because there is still a word left, and this word needs to be accounted for in the parsing process. So, now we come to this point about parsing structural ambiguity. If the sentence is I saw a boy with a telescope, the grammar is S goes to NP-VP as usual. NP can be article and noun, or article, noun and preposition phrase. or simply a pronoun. Verb phrase also can be verb, noun phrase and preposition phrase, or verb and noun phrase. Article can be a and the, noun can be boy and telescope. Our vocabulary is limited here, only two nouns, boy and telescope. Pronoun is I, verb is saw. All right. So, now let us look carefully at these rules. Okay. So, these first the second rule, for example, says that we have a wide variation possible in constructing noun phrases. They can be simply article noun combination, or they can be article noun combination where the noun itself is modified by a preposition phrase. Preposition phrase becomes a qualifier for the noun, or the noun phrase itself can be a pronoun. Similarly, we have variety possible on the verb phrase. All right. So, we have verb and noun phrase and the preposition phrase. The preposition phrase can now get attached to the verb as is shown in this combination, and thereby signaling the fact that the verb phrase has a preposition phrase embedded, which is a constituent. And here V noun phrase is simply the depiction of the case where the verb is a transitive verb with taking an object, and so on. So, let us see if you understand this particular point, that these two rules, namely article going to article, noun and PP, and verb phrase going to verb, noun phrase and PP, is the potential ground for multiple parse trees or structural ambiguity. The preposition phrase can be attached to noun, or preposition phrase can be attached to verb, and the grammatical rules, these two grammar rules, capture that phenomenon. Now, it must be clear to you as I explain this, that ambiguity is unavoidable in natural language, and sentences have different structures. A particular sentence can have multiple structures, and when these multiple structures obtain, different grammatical rules come into play, and a close examination of the grammatical rules capturing the language or language fragment is sufficient to tell us that there is potential ground for ambiguity. And when multiple sentences, multiple parse trees come out from a sentence, what do? We have to choose one, and we choose this one by a scoring mechanism through probability. Looking at the slides, two possible parses for this sentence. I saw the boy with a telescope are these. PP is attached with the verb, that is, I used a telescope to see. So, here is what we see in the form of a bracketed structure. Now, S is the starting symbol. So, here we see that this S is composed of a noun phrase which finishes here, and a verb phrase which is more complex. Now, this particular verb phrase has the main verb saw, a boy with a telescope. All right. Now, we ask this question, where is with a telescope? With a telescope is a preposition phrase, no doubt, but what does it attach to? Okay. What does it attach to? We see that this preposition phrase is in the scope of this noun phrase. Okay. In the scope of this noun phrase, no, I am sorry, the preposition phrase is in the scope of the verb phrase, and therefore, this attaches to the verb and I have the telescope. In the other case, the preposition phrase is attached to the boy, because it is contained within the noun phrase, not in the verb phrase. It is contained in the verb phrase, but more so within the noun phrase, because its immediate parent is the noun phrase. So, this is the attachment to boy. There are two ambiguous parses. By the way, this kind of bracketed structure is another alternative representation for the parse tree. We are used to seeing the tree. The tree has the non-terminal, then expanded non-terminals, then terminal and so on. But the same thing can be expressed by creating bracketed structures. A particular enclosing of bracket finishes a phrase. Now, we take this ambiguous sentence and run the top down parsing algorithm. We first have the starting state input pointer at 1, no backup state. S is expanded by NP and VP, no backup state. NP and VP, no, I am sorry. We use there is no backup state because S can be expanded only in one way. Now, we have to use NP goes to article noun or article noun preposition phrase or pronoun, and we have to take up the textually first rule, which is article and noun, and there are backup states which are article noun preposition phrase and pronoun. So, the backup states are article noun preposition phrase verb phrase and pronoun verb phrase with input pointer at 1. So, these states are in the waiting. In case this state fails, the alternative states will be brought to the stack. So, this of course fails because article does not match anything. We do not also bring the state A because again it is fronted by art, which will not be able to match anything on the input data. Now, pronoun VP is brought in. So, I is consumed, input pointer moves to 2. Now, VP is expanded by VNP, PP, VNP, PP, and VNP is the rule in waiting. Now, the verb is consumed, saw, that brings NP, PP exposed on the stack. Now, NP has to be found out. NP is expanded by article noun preposition phrase, article noun preposition phrase, NP is expanded by article and noun. Article noun preposition phrase is in the waiting, similarly pronoun is in the waiting. Now, the word A on the input is consumed by article, that makes N and PP exist on the stack. Input pointer is moved to position number 4. At this point, noun is used to consume boy. When boy is consumed, then we find that PP and 5 exists on the stack. PP and 5 exists on the stack before that step boy was consumed. Now, we have P and NP here. Okay. Now, continuing in this way, where the first step was 1 and the sixth step had exposed N and P. Now, we have article N and PP and the input pointer is at 3. Backup states are article N PP with input pointer at 3, pronoun PP at input pointer at 3. Again, we consume A, that brings PP, that brings NPP with 4 for the input pointer position. Now, PP is exposed, PNP comes in, NP comes in, with is consumed. Similarly, all the NPs are developed, and then finally, telescope is consumed and there is no symbol on the stack. The input data is over and that finishes parsing. So, what is seen here is that we can have multiple parses if we do not stop at a particular stage of processing where all the input symbols have been consumed and the start symbol also has been popped from the stack. Okay. So, this is a particular way of parsing which attaches telescope to the buoy. Okay. That is because in the sixth step we had V, N, P, 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 okay, I am sorry, V, N, P and P, P, and N, P, P, P came, N, P and P, P came, and V, N, P, P, P path was pursued. This V, N, P, P, P path was pursued, and that finally led to telescope being consumed at the final step and S also getting popped from the stack. So, this is the path which is pursued with V, N, P, P, P. Now, if we take the other path which is with the state waiting in the backup stack V, N, P and 2 and follow similar process of expansion, we will get the parse tree where the preposition phrase with the telescope is attached to noun. All right. We can see here step 5 says verb attachment rule is used, and we have followed this path completely to get the parse tree finally. Now, this is the example where one of the parse trees has been produced. One of the parse trees is produced. All right. So, this shows how the stack based top down parsing can handle ambiguity by following one particular state on the stack up to completion and then revisiting the backup states and seeing if the parsing can be completed from those backup states. So, that would produce the other parse trees. So, I suppose this particular point is clear about how ambiguity can be handled in parsing, in top down parsing. The possibility of pursuing a different path with a different state always exists in top down parsing. The stack contains that information. Finish the parse, then revisit the stack, see what kind of states obtained there and follow those to finally finish the parsing process. And if there are multiple parses possible from that sentence, they will come out by this procedure. Now, we move to some observations, which is that top down parsing gave us the verb attachment parse tree. I use the telescope. To obtain the alternate parse tree, the backup state in step 5 will have to be invoked. Is there an efficient way to obtain all the parses? That is an interesting question to think about. Now, how does bottom up parsing deal with ambiguous sentence, and does it have the capability to produce multiple parse trees? This is the question we now pursue with the same example. I saw a boy with a telescope. Note the between what positions, 1 before I, 2 between I and saw, 3 between saw and I, and so on, and finally 8, which should have been after telescope to indicate the end of sentence. Okay. So, since there are ambiguous situations and multiple parse trees are possible, we follow this color convention: blue for normal parse, green for verb attachment parse, and purple for noun attachment parse, red for invalid parse. So, when we have I saw a boy with a telescope, the first stage produces noun phrase and pronoun. All right. So, first we see that between 1 and 2 we have resolved the pronoun and NP is resolved with pronoun. The dot moves over pronoun. In S, the dot has gone over NP. Now, VP has to be found out. These suffixes have to be noted. NP12 and pron12 says that between 1 and 2 we have found a pronoun and a noun phrase. S1 question says that there is a sentence beginning at 1, ending at where we do not know. NP12 is fine, we have found a phrase between 1 and 2. BP begins at 2, ends at where we do not know. In the next item set, we have resolved the verb with saw, and thereby VP has completed the work of finding a V. Now, an NP has to be found starting from position number 3. Now, ambiguity situations crop up. Two rules are applicable in this situation. So, we can also have the verb phrase with V resolved and NP and PP to be found. When we go to the next word, which is A, an article has been found, thereby the noun phrase has completed the work of article, a noun has to be found, or a noun phrase has completed the work of noun and the noun and preposition phrase has to be found. Now, boy is resolved. So, a noun has been found between 4 and 5, that resolves a noun phrase between 3 and 5, a boy, and it also resolves partially another noun phrase which is article and noun, but we have to find a preposition phrase after that. Now, what we see is that since we have found a noun phrase with article and noun, we can complete this verb phrase here. Okay. So, that is why the noun phrase, the dot moves over this noun phrase and a noun phrase has been found between 3 and 5. 3 and 5 is a boy, and thereby a verb phrase is resolved between 2 and 5, saw a boy, and thereby a sentence is resolved between 1 and 5, I saw a boy. And it is indeed true, because I saw a boy is a complete sentence segment or a complete sentence actually within the whole sentence. But at the same time, since the noun phrase has been found, we can move the dot over the noun phrase in this production rule, and now it exposes PP. So, we have found V and NP, which is saw a boy. Now, we have to find a preposition phrase. Now, here though a sentence has been found, we cannot finish the parse because there are still words remaining in the input sentence. Proceeding further, we have now found a preposition with. So, a preposition between 5 and 6 is found, P 5 6. We are waiting to find a noun phrase to complete the preposition phrase starting at position 5, and this we have found partially, because now we have found an A and an article between 6 and 7 is found. So, that now wants a noun to be found at position 7 and a noun phrase with article and noun, or a noun phrase with article and noun and preposition phrase is waiting to be completed. At this point, we find a telescope, which is fine. Then this noun phrase from 6 to 8, a telescope is completely done. A is completely done, yes, and that will finish the preposition phrase with a telescope between the position 5 and 8. With a telescope is a complete preposition phrase. So, that will complete this verb phrase here. Okay. This or rather this noun phrase here, a boy with a telescope, 3 to 8, and when this is done, this verb phrase between 2 and 8, this verb phrase between 2 and 8 will be finished. Okay. But it will be finished in two ways. One is a verb between 2 and 3 and a noun phrase between 3 and 8, or a verb phrase which is composed of verb between 2 and 3, noun phrase between 3 and 5, a boy, and a preposition phrase from 5 to 8. So, now the sentence gets over with noun phrase from 1 to 2 and verb phrase from 2 to 8. However, the verb phrase from 2 to 8 is completed in two different ways, either by PP attachment to the verb or by PP attachment to the noun a boy, this particular situation. Okay. So, this shows that bottom-up parsing also can handle ambiguity by maintaining within its item set or the chart all the applicable rules. Okay. So, these bigger arcs are indicators of larger parses and in larger phrases, and in each phrase we maintain the indications of ambiguity. For example, this phrase has two possible structures: verb, noun phrase, preposition phrase, or verb and noun phrase, where the noun phrase itself is noun and preposition phrase getting attached to the noun. Now, we move forward, and there are some observations on bottom-up parsing. Both noun attachment and verb attachment parses obtained by simply systematically applying the rules. So, this we have seen in the parsed processing itself. There are the indications of the rules which are applicable. Numbers in subscript help in verifying the parse and getting the chunks from the parse. So, I suggest this exercise to you. The man saw the boy with a telescope is the input sentence, and the grammar is given previously. We first compare the performance of top down and bottom up parsing on this ambiguous sentence. Comparison means discuss which strategy maintains more cleanly the ambiguity indications. How is the ambiguity indication maintained in top down parsing? This is maintained very definitely and cleanly by backup states on the stack. How is ambiguity indication maintained in the bottom up parsing? It is maintained by multiple items in the item sets or the charts on each arc between two words. Okay. So, this is the data structure which maintains the possible parse tree completion paths, the potential trees which can come out of the grammatical rules. So, both of them maintain the ambiguity indications in their own way, and after that the processing can reveal the ambiguity. Now, in top down parsing, a revisiting of the stack for all the backup states is necessary to obtain the ambiguities. Whereas, in bottom up parsing, the whole ambiguity situation is worked out. Both the trees or all the trees, because of ambiguity which can come from the sentence, are maintained in the charts. Okay. So, an amount of rereading of the charts is required to obtain the trees, but one will not have to expand the rules again or resolve the data or the words with the non-terminals to obtain the parse trees. In the top down parsing, regeneration of the trees are required. So, one can say that in top down parsing, the development of the tree has to be done. The development of the tree other than the one obtained has to be done, but in bottom up parsing the trees are already developed, they are there in the charts, they only have to be retrieved. In top down bottom up parsing, it will be an interesting question to investigate how ambiguity is handled and multiple parses are produced. So, with this we close our discussion on deterministic parsing. We have seen top down, bottom up and top down, bottom up chart parsing. We have seen also how ambiguous sentences are handled. All this is fine. Now, an important deterministic algorithm here is a CYK algorithm. CYK algorithm is a dynamic programming based parsing algorithm, which finds its usage in probabilistic parsing also. So, this we did not do here, it will be done along with probabilistic parsing. We begin probabilistic parsing now. So, here is a very useful resource called the bracketed structure, and these bracketed structure are the trees actually for the sentences, and a collection of such bracketed structures forms what is called the tree bank corpus. If you look at this sentence, come July and the IIT campus is abuzz with new and returning students. This is a complex sentence because it has a clause embedded, come July, and the IIT campus is abuzz with new and returning students. Now, the IIT campus is abuzz with new and returning students is a complete parse tree, and the bracketing shows the inherent structure. So, let us go over this slowly. The is a determiner, it is resolved this way, and the bracketing shows dt goes to the. IIT has an adjectival role here. So, it is an adjective for the campus which is now. The IIT campus can be combined together to form a noun phrase which is shown here, NP. Now, when NP is over, it only requires a verb phrase VP to complete the sentence. Let us see, is an auxiliary, there is an adjective phrase abuzz with new and returning students. So, abuzz with new and returning students is a complete adjective phrase. So, this adjective phrase along with the auxiliary verb which comes before the adjective phrase completes the verb phrase. Now, the verb phrase and noun phrase together completes a sentence. Let us take a look into the structure of the adjective phrase itself. Adjective phrase surely has an adjective as the head which is abuzz, and abuzz is taking a preposition phrase after this which has with as the preposition. The tag in is used for preposition in the tree bank corpora. Now, this adjective new and returning is a complex adjective phrase with two adjectives new and returning linked with and. Returning is a gerundial verb as indicated by VBG, but it actually has an adjectival role. That is why it can combine with an adjective through a conjunction CC and produces the adjective. Now, this adjective along with the adjective phrase along with students, which is a plural noun, forms a noun phrase. With and the noun phrase that is preposition noun phrase forms a preposition phrase, which when combined with adjective phrase, which when combined with an adjective produces the adjective phrase, and this adjective phrase combined with auxiliary verb produces the verb phrase. So, auxiliary verb followed by a noun phrase is a followed by an adjective phrase or adjective is a very classic case of a verb phrase. So, weather is hot, the day is cold, John is well, my sister is studious. These are examples of cases where auxiliary and a predicative adjective together forms a verb phrase. It is a very common construction in English language. So, this bracketed structure is nothing but the tree, parse tree itself, written in a linear fashion. Now, we are discussing probabilistic parsing. In probabilistic parsing, what we are interested in is the probability of a parse tree. In probabilistic parsing, the entity of interest is the probability of the parse tree. And as in other branches of statistical natural language processing, we make use of what is called the noisy channel model, which is shown in the slide. The source sentence passes through a noisy channel and produces the target parse. The production of multiple parse trees from the source sentence can be looked upon as injecting of noise as the sentence comes over the pipeline and transforming to the parse tree. So, T star is the desired parse tree, the best possible parse tree. How is the best possible parse tree found? By maximizing the probability of the tree given the sentence, and that is why this argmax computation. T star is nothing but argmax T P T S. We apply Bayes theorem here, and P T S, P T given S is turned into P T into P S given T. So, likelihood of the sentence given the tree and the prior probability of the tree. Now, a very interesting thing happens. The likelihood of the sentence given the tree ceases to be uncertain. It is no more uncertain. Given a parse tree, the sentence is uniquely determined. We simply have to traverse the leaves left to right, and the sentence is completely determined. So, given the tree, there is no uncertainty with respect to the sentence. That is why P of S given the T is 1. So, this produces an interesting expression. T star, the best possible parse tree, is nothing but the tree with the highest probability, which is intuitive. So, get the sentence, get all its parse trees, and the tree which has the maximum probability is the best possible tree. Now, of course, this has placed the ball in another court. So far, we were interested in finding an expression for the best possible parse tree, that we found in terms of probability value, and the expression now demands that the probability of the tree be calculated. What is the meaning of probability of a tree? We proceed to discuss this question. So, here is a side discussion. A collection of text is called corpus. It is used for collecting various language data. With annotation, more information comes in, but the manual labor is intensive. Practice that is followed in the field typically is label automatically, but correct manually. The famous Brown corpus contains 1,000,000 tagged words. Switchboard corpora is also very famous. It contains 2,400 conversations, 543 speakers, many US dialects annotated with orthography and phonetics. The next question, which is also a really an issue on the side, but important nonetheless, is the question of discriminative versus generative model. Our W star can be found from probability of W given S s, where S s is some quantity, W is another quantity. The relationship between W and S s is that there is a noisy channel and one is the input, other is the output. W star can be found directly from P W given S S, which is called the discriminative model. We compute directly from P W given S S. The other competing model is the generative model. We compute from P W into P S S given W. Now, the debate between discriminative and generative model is not yet over. The NLP community comes up with different arguments of why one approach is better than the other, or why one approach is worse than the other. So, this debate is ongoing. Language models we have discussed already before. There are n-grams, there are probabilistic, stochastic, context-free grammars. Now, context-free grammar, probabilistic context-free grammars are a very powerful mechanism for capturing language regularities. Simple probabilistic models are capable of handling recursion. A CFG with probabilities attached with the rules. Rule probabilities imply how likely is it that a particular rewrite rule is used. We elaborate these ideas as we go ahead. Now, why probabilistic context-free grammar? These are intuitive probabilistic models for tree structured languages. All natural languages are tree structured, sentences embed sentences, and so on. Algorithms are extensions of HMM algorithms. That is a very important powerful point. Hidden Markov model has been understood very lucidly in the probabilistic community, signal processing community, electrical engineering community, and now statistical NLP community. And powerful algorithms for finding the probability of the observation sequence, finding the probability of the automaton, learning the parameter values for the automaton. These have been investigated thoroughly, and interesting results have been obtained. Now, there is interesting correspondence, very interesting correspondence between HMM and probabilistic context-free grammar. We will show that algorithms in HMM translate directly to algorithms in probabilistic context-free grammar. So, these are the powerful ideas which can be used to produce the parse trees and their probabilistic calculations. Now, the PCFGs are better than n-gram model of language modeling. We will justify why. Now, first we give a formal definition of PCFG, probabilistic context-free grammar. A PCFG consists of a set of terminals Wk, k equal to 1 to v. For example, if our vocabulary is child, teddy, bear, played, then this is the set of Wk. A set of non-terminals Ni, I equal to 1 to n, Np, Vp, Dt, etc. the non-terminals. A designated start symbol N1, which is a spatial status in the parsing process. A set of rules Ni going to zeta j, where zeta is a sequence of non-terminals and terminals. For example, Np goes to Dt Nn, a corresponding set of rule probabilities. So, all right. So, PCFG consists of terminals, non-terminals, start symbol, rules, and probabilities. So, PCFG is nothing but CFG augmented with probabilities on the rules. Now, the rule probabilities are such that sigma for all I, sigma over I of p n I going to zeta j is equal to 1. What does it mean? If a non-terminal expands into multiple sequences, then the sum of the probabilities of these different production situations must be equal to 1. So, for example, probability of Np going to Dt Nn is 0.2, probability of Np going to Nn is 0.5, Np going to Np and Pp is 0.3, and we can see that all of these sum up to 1. Now, what is the meaning of this expression P Np going to Dt Nn equal to 0.2? This means that 20% of the training data parses use the rule Np going to Dt Nn. So, when we are parsing the corpora, 20% of the time we find that noun phrase consists of Dt and Nn. Noun phrase consists of an article and a noun. So, that is why the probability value is 0.2, and you can possibly see that one can easily compute this probability by keeping track of the count of how many times this Np going to Dt Nn rule was invoked, as opposed to other instances of NP replaced by other sequences of terminals and non-terminals. So, how many times have we applied NP going to DTNN as opposed to NP going to NPPP or NP going to adjective phrase NP or NP going to simply noun. Now, here is an example of a probabilistic context-free grammar rules capturing the language, a fragment of English language. S goes to NPPP, probability is 1.00. There is no doubt that S can be expanded only this way for declarative sentences. If there are interrogative sentences, then a VP will begin the sentence. So, NP goes to S goes to NPPP is 1.0. We are dealing with only declarative sentences. NP goes to DTNN has the probability 0.5. NP goes to NNS 0.3. That means NP consists of a plural noun. That happens 30% of the times in the corpus data. NP goes to NP and PP, that means a noun phrase consists of noun phrase followed by preposition phrase, that happens 20% of the times. Preposition phrase is always preposition and noun phrase, that is why probability 1.0. Verb phrase can be verb phrase and preposition phrase 60% of the time. Verb phrase can be a verb in past tense and a noun phrase 40% of the time. Determiner is the 1.0. We are assuming there is no other article or I am sorry, there is no other determiner like that and this. There is a single noun which is gunman. No, there are two nouns, gunman and building, each with probability 0.5. That means the distribution of gunman and building in the corpora as noun is half-half. VBD, it is a past tense verb. We have only one past tense verb, sprayed. The probability is 1.0 because this is the only occurrence of the past tense verb. Plural noun is bullets, again 1.0. So, this is a fragment of English language. On the right hand side, we have placed what are called lexical rules. Okay, these are all rules which go to a terminal or a vocabulary of the language, whereas these are syntactical rules. They capture the grammar of the sentence. For example, how is a noun phrase formed? DTNN, NNS, NPVP. How is a verb phrase formed? Verb phrase and preposition phrase, or a past tense verb and noun phrase. So, this is capturing the syntactical rules, this is capturing the lexical rules. Now, the gunman sprayed the building with bullets. If this sentence is taken, then we can have one parse tree which is shown here. This is a parse tree starting with sentence S consisting of noun phrase and verb phrase. In the noun phrase, we have determiner and noun, the gunman. The verb phrase itself can be verb phrase and preposition phrase. Here the preposition phrase is attached to the verb, who with bullets is attached to spray, and the verb phrase is consisting of a past tense verb BBD, sprayed, and a noun phrase DTNN, the building. So, spray the building is the verb phrase and the building is the object for spray. With bullets is the preposition phrase attached to the verb. All right. So, this is one parse tree. The other parse tree is where the preposition phrase gets attached to the building, okay, as is shown here. So, NP contains the NP and PP, the whole thing forms a constituent of the verb phrase. So, there are two possible parse trees and they have different probability values, as we will see in the next lecture, and we will choose the tree which has the highest probability value. So, we compute some interesting probabilities and proceed with the probabilistic parsing in the next lecture.